Hello class. Today we're going to talk about the central limit theorem. Okay, this is the stuff that we were going to talk about previously before spring break, and then the whole school shutting down because of the outbreak, whatnot. This was supposed to be on the last test. So we're going to talk about the central limit theorem. Now, before I do that, let's go ahead and remind ourselves what we were doing in chapter 6. We were dealing with normal distributions. So this is just a review. You should have something similar to this in your chapter 6 notes. But a normal distribution looks something like that. And if down here is my axis, we have some mu, our mean, our population mean, and we have some standard deviation, population standard deviation for these normal distributions. And what we were doing previously was we were finding the area underneath the curve, okay? So let's say I wanted to find that area right there, okay? We had some calculator functions that we would use to compute that area. We're going to need those same calculator functions for the central limit theorem in chapter 7. Now it was normal CDF. And if you recall, there was a normal CDF and a normal PDF. Remember, we are not going to use the normal PDF. We should only be using the normal CDF. Okay, so when we type things into normal CDF, I showed you guys that we could either use z-scores or we don't have to use z-scores. We could just use the raw numbers. Okay, so normal CDF. If you remember the inputs, it was the lower bound, comma, the upper bound, comma, the mean, comma, the standard deviation. Alright, so and if you remember, if we did the lower bound, and it was like going off to negative infinity, kind of like the graph that I just had here. Let me redraw it real quick, where I was finding all of that area there. We would use a really large negative number for the lower bound, so maybe like negative 1,000. And then for the upper bound, if we were doing it the other side, we're finding the area all the way over here, we would just use a really large positive number, 1,000, 10,000, something like that. Okay, now remember how to use this normal CDF. We're gonna need it for chapter 7, lower bound, upper bound, mean, and standard deviation. Now there was another calculator function that we used to find percentiles, okay? If I told you what represented the 95th percentile, we would do inverse norm of our percentage. What is the percentile you are trying to find, comma, mean, comma, standard deviation. Now, if you're having trouble finding these, remember, these are located under, you gotta hit your second button, and then you hit your, is it the vars button? Let me see, my calculator somewhere around here. Yeah, it is the vars button. Okay, so second button, vars button, it brings up your distributions. Normal CDF is number 2. Inverse norm is number 3, okay? So that's just a quick review of what we're doing in chapter 6. But now let me go ahead and explain what the central limit theorem says. Now, in 7.2, we skip over 7.2. It goes through another central limit theorem. We're not going to talk about that. It's for sums, okay? The central limit theorem that we're going to talk about here, so CLT for central limit theorem, so we don't have to write it all the time. Central limit theorem for means. So for the averages, okay? So one thing that you're going to have to do is have my notes out in front of you. Because I'm limited to board space, I can't write everything on the board. So as you guys are following along with this video, either have the notes in front of you printed out, or at least have them open on the screen, so that way when we read these definitions and go through them, you can just read them with me, and you don't even have to write them down because you have them in a Word document. Okay, so it says, suppose X is a random variable. Okay, what that means is, say we're measuring something about a population. The random variable could be the time it takes somebody to get to work. Okay, number of times they go to the bathroom in a day. Let's see, the average or the height of a person. Okay, whatever the random variable is, it has some average, some mean. Okay. It also has some standard deviation, sigma. Now, what we're going to do, if we have some population, now I'm just drawing a random shape here. Everything in here constitutes my population, okay? And it has some average and it has some standard deviation. These are population parameters. Now, what it says is, suppose that we select samples of size n, okay? We are going to select, let's see, right here, whatever it is. Here's sample 1, okay? They all have size n, so every sample is size n. Okay, you're gonna fix the number of people or things you're gonna pull for each sample. Now this sample, it's gonna have some x bar 1 for sample 1. Over here, if I pick another sample, sample 2, it's gonna have its own average, x2 bar. Over here, if I have a third sample, sample 3, remember these are all size n. They all have the same size. Even though I'm not drawing them the same size, they do have the same size. This is going to have its own average, okay? Now, if we keep taking samples of size n, and we compute all of their averages, what this does is it creates a normal distribution for the averages. So, normal distribution for the means. So if I were to keep taking sample size of n, and I keep finding their sample means, and I were to plot all of their sample means, it's going to be approximately normal, okay? And that's what the central limit theorem is saying. We could, if you keep pulling samples of the same size, their averages, the sample averages, form a normal distribution curve. Okay, so now let's look at the statements from the central limit theorem. So I was just explaining the first parts of it. Suppose that we have a random variable, and then we have some distribution. We're pulling samples of size n. Then we know the following are true. The first one, the average or the mean of the sampling distribution for x for big X bar, okay, big X bar, our random variable was X, but our sampling distribution is, we're going to call it X bar, is the average of the sampling distribution is equal to the population average, okay? So what we're doing is we have some population, okay? And then we're going to keep pulling samples of size n, and from that, using their means, we're going to make a new distribution. From taking all those averages, if we find the average of the averages, the mean of the means, it's equal to whatever the population mean is. Okay? Now, let's go ahead and see why this is true. We're going to just think through it, talk about it. Now, in sample 1, okay, we found it to have an average, whatever it is, X bar 1. Sample 2 had some average. Sample 3 had some average. And we pull many, many samples, all size n. Okay, now let's talk about this a little bit more concretely. You might be able to understand this. Let's say we know the average age of CLC students. Mu is equal to, now I'm making this number up. I have no idea what this number is. Let's say it's 24.3 years. The average age of CLC students is 24.3 years. So now let's say we go around CLC. We have a sample size of 100. So what we're going to do is we're going to go around CLC. We're going to ask people, 100 people, what their age is. Then what we're going to do is we're going to compute, out of those 100 people, we're going to compute the sample average. The sample average for our first sample, again, I'm making this number up. Let's say it's 22.9 years. It's a little bit smaller than our actual population average. Now again, we go around CLC, we ask 100 more people about their age, and then we compute the average of their ages. Say we got 25.1. Okay, I just made it up again. Now this time it's over that number a little bit. Okay, it's over our actual population average. Now, we do it again. We're going to keep doing it many, many times. But let's do it one more time. And we ask 100 people what their age is. Out of those 100 people, we find the average age is 24.5 years. Okay? It's still over, but it's almost exactly the population average. Okay? Now, we have some that undershoot the actual population average. We have some that overshoot the actual population average. We have some that are about equal to the actual population average. So the central limit theorem is saying is if I find the average of all the averages, this is going to be equal to the actual population average. Okay? Now here's why. Think about how we find averages. We add up all the values and we divide by how many there are. We pull samples, many samples, okay? They each have their own sample mean. Some undershoot, some overshoot, some are about the same. The ones that overshoot compensate for the ones that undershoot. The ones that are about the same, well, they're about the same, okay? With all this overshooting and undershooting compensating for each other, if you take many samples, the average of all of the averages should equal the population average. That's what the central limit theorem is saying, okay? Now that's just part one. There's a part two. Let's see. It says the standard deviation for the sampling distribution is sigma of our sampling distribution. The standard deviation of our sampling distribution is equal to whatever the standard deviation was for the population divided by the square root of n. Okay, that's it. Just a slight tweak to the formula. So when you guys are finding like normal CDF and you guys are doing that calculations, well, the lower bound, upper bound, and mean all stay the same. The only thing that changes here is you got to divide your standard deviation by the square root of your sample size, okay? All right, now there's a third part of the central limit theorem. It says the sampling distribution is approximately normal for n is greater than or equal to 30. That's our cutoff point. You have to take a sample size of at least 30 to assume the central limit theorem that the averages form a normal distribution. Okay? Now, I know problems in your homework will, like online, some of them will pop up where the sample size is not above 30, but they want you to still use the central limit theorem. That's okay. The sample size does not have to be greater than 30, but we definitely should try, if we were to actually do a statistical study, we should definitely try to get over 30 data points if we want to use the central limit theorem. Now, if we can apply the central limit theorem, we could say that our sampling distribution is approximately normal. Oh, sorry, not our sampling distribution. Our normal random variable. Our random variable is approximately normal. It doesn't matter what distribution this has. If it meets the requirements of the central limit theorem, we could say it's approximately normal with whatever the mean was for this random variable, the standard deviation divided by the square root of n. Okay. Now, sometimes the definitions, the standard deviation of the sampling distribution sometimes is called the standard error of the mean. Now, let's think about something real quick, looking at the standard deviation for the sampling distribution. Remember, this is the standard deviation of the averages, okay? And when we find the average of the averages, it should equal the population average. But now, let's say our sample size gets bigger and bigger, okay? If our sample size gets bigger and bigger, the sample average should get closer and closer to the population average. Because eventually, if you make your sample size large enough, it will be the entire population. So then your averages, your sample averages, should be exactly equal to the population averages. So then if they're exactly equal to the population average, there should be no standard deviation. And if we look at this formula right here, if n keeps getting bigger and bigger and bigger and bigger, let's say for just argument's sake, sigma is equal to 1, divided by, if this keeps getting bigger and bigger and bigger, if it's 1,000, this is 0.001, If it's a million, it's 0.000001. So as this number gets bigger, the standard deviation or the standard error, the mean, gets smaller. It gets closer and closer to 0. And that's what you should expect when you get closer and closer to having a sample size equal to the population. Okay, now, one more formula. Real quick formula. You've seen this formula before. Calculating z-scores. The old formula was just x minus mu divided by sigma. Now, if you want to take a data value, say we're using the central limit theorem here, here's the new equation that your z-score is equal to x bar minus mu divided by sigma divided by the square root of n. Okay? And notice how it changed from x to x bar. Okay? This is when I'm finding the z-score of an individual data value. This is when I'm finding the z-score of a sample mean. Okay? So that's why we have to divide the standard deviation. Right here would be the standard deviation. So as you can see, if I were to put that right there, you'd have x bar, and you got x bar right there. You're using the correct sample average and the correct standard error. Okay, this is going to be important. In section 7.3, we talk about when to use the central limit theorem as opposed when not to use the central limit theorem. Okay.